Hello, good morning. This is Shivashankar Rajamani from KSR College of Engineering, and we are celebrating 25th year of academic excellence. Today, I am going to deal about optical fiber communication. In that optical receivers, so I will be dealing about Avalanche Photodiode. So this is my content page, introduction, then principle of photodetector, constructions, material used, working, special design features, equivalent circuit, advantage, disadvantage, and comparison of two photodiodes, that is avalanche photodiode and pin photodiode. This is the practical application of your avalanche photodiode, how it looks like. Construction, so it is heavily doped P plus region, the top contact thin enough for light to enter. So it is the place where light will be entering. So P plus refers to its heavily doped, and the next region will be your intrinsic region. It is pure form of semiconductor. It is a place where absorption plus drift region takes place. And third layer will be a lightly doped P region, which will be very near to the heavily doped N plus region, where the multiplication process generally takes place. Here the multiplication region is very near, and the last will be your contact of metal electrodes. So this will be your construction. Then material used, we have two types of material used, one for telecommunication purpose, which has the wavelength of 1.3 micrometer to 1.5 micrometer. For heavily doped P plus region, it is indium phosphate. Then pure semiconductor is made up of indium gallium arsenide, and P material is made up of indium gallium arsenate phosphate. Then heavily doped P plus is made up of indium phosphate. Then for case 2, which is purely a silicon based avalanche photodiode, which will be in the used for visible range approximately from 1 micrometer. So here it is P plus region is silicon, then intersonic is pure silicon, then P region is also silicon, then heavily doped N plus region is also silicon. Here all the materials or in the case 2 will be silicon. The working of your avalanche photodiode, first we will go look into the bias. So generally all your photodiode will be connected in reverse bias. The avalanche photodiode operates under large reverse bias voltage, which is very close to the breakdown region. So this is the main condition for avalanche photodiode. It creates a strong electric field across the depletion. Here when light enters in the P plus region, photons are absorbed in the semiconductor. So light photons which has sufficient amount of energy will be absorbed in the semiconductor, which creates primarily electron hole pair. This electron hole pair will be absorbed in the carrier separate and drift region. This will have a strong electric field which will be moving with a very high speed. This electron drift towards N plus region and holes starts to move towards P plus region. Next is carrier acceleration in high field, where the multiplication process takes place. The electrons and hole have high kinetic energy while moving in high field. Here the multiplication process takes place. The energy which is having the electrons which collide with the crystal lattice, which will generate more number of electron hole pairs. So one electron will hit the crystal lattice, and that will make 2 electrons, and 2 will make 4 electrons, 4 will make 8 electrons. So this process will, it's a continuous process, and this process is called as impact ionization. Here newly carried large number of ions are being produced, that's why it's called as impact ionization. It also accelerates and cause further ionization. The chain reaction occurs which cause the multiplication process. This will be in the order of 100 to 200 for avalanche photodiode. Then collection of multiplied carriers. The multiplied carriers are collected at the contacts. The external circuit sees the current equal to the primary photocurrent times the avalanche photodiode gain. Here the multiplication factor is approximately of 100. The output and external circuitry. The multiplied photocurrent is converted into useful voltage or current by the using load resistor, and that will be given to the pre-amplifier. Here the generally pre-amplifier is a trans-impedance amplifier. So because of this trans-impedance amplifier, it is stable, low noise, high output voltage supply is essential. Because this avalanche photodiode will be generating again a noise which is more than pin photodiode. Here it is the multiplication gain M, it is the ratio of total output current to the primary photocurrent. So M is equal to I total divided by I primary. Here the linear avalanche photodiodes usually have the gain of tens to few hundreds. It depends upon the bias. The gain in the order of, for linear mode it is from 10 to 100, sometimes it goes up to 200 in special design. So you have an excess noise. This avalanche multiplication process is a stochastic process. So this will add more noise than pin photodiode. The noise depends upon ionization coefficient of electrons and holes. And this is the circuit which explains the avalanche process. This P plus region is connected with negative, and P region, that is positive of your supply, is been connected to N plus region. So this electron, when light falls in I region, so electron hole pair will be generated. This electron hole pair, electrons will be start moving towards N region and holes will be start moving to P region. This electron has a sufficient amount of energy and that will collide with the crystal structure. This one electron will have two electrons and 2 will make 4. So that is the process which is being shown in the thing. Here at the depletion region of P and N plus region, you have your impact ionization. That depletion region is the main region where your impact ionization takes place. And this is the same thing where the light falls on it. It will produce electron hole pair which is called as impact ionization. Then special design features of avalanche photodiode. So in order to have a large number of noise to protect, we use guard rings, a circular P plus region at the peripherals to prevent premature edge breakdown. Then you have an anti-reflecting coating on the top of the window to increase photon entry efficiency. Thin multiplication layer ensures strong field with minimal carrier transit time. Then material engineering, you have a wide band gap of multiplication, narrow band for absorption, which reduces excess noise. The electric field will be in the order of 2.5 into 10 power 5 volt per meter to 3 into 10 power 5 volt per meter. So this will be the maximum amount of electric field which is being produced inside the avalanche photodiode at the impact ionization place. And this is your equivalent circuit of avalanche photodiode. So it consists of IP, a current source, and a detector current source. Then you will have a parallel photo capacitor, that is diode capacitance, and you have a series resistance RD. This PH represents photocurrent generated by the detector, where CD represents the detector capacitance, This ID represents the dark current, then IN represents multiplied noise current in avalanche photodiode, then RD is the bulk and contact resistance. This is the equivalent circuit for avalanche photodiode and PIN photodiode. Then advantage of avalanche photodiode, it is more sensitive with high range, and second is quick response time. It detects low intensity light or high sensitivity. These diodes are applicable here. The gain level is very important as it operates in high voltage. Through lower reliability means that they are frequently less convenient to utilize. A single photon generates a huge number of charge carriers. Disadvantage of avalanche photodiode, this requires high operating reverse voltage. The output of this diode is not linear, high range of noise, it is not used regularly because of low reliability. It uses high reverse bias for its proper operation. And this is the comparison chart for avalanche photodiode and PIN photodiode. The construction itself, it is P plus I, then Pn n plus region in avalanche photodiode, whereas you have P plus I and n plus region. Response time is very high for avalanche photodiode, response time is very low for PIN diode. Output current is low, the multiplication of carriers can cause amplify current value. The internal gain is around 200 dB, the internal gain is less than 1 gain. It's avalanche photodiode which has high temperature stability, whereas PIN photodiode has low temperature stability. Then reverse bias voltage is very high in avalanche photodiode, whereas reverse bias voltage is very low in PIN photodiode. The amplifier is not necessary because of available gain, because it has gain of 200, whereas for PIN diode it is compulsory to have an amplifier. Avalanche photodiode has high temperature stability, whereas PIN photodiode has low temperature stability. And I need your feedback and suggestions. You can subscribe to my channel. Thank you.